Okay, so if we consider the Eulerian form and converting it to the Lagrangian description, we take note that we simply make use of uh, a chain rule approach here to come up with a okay a capital X here. Okay, so we just apply uh, chain rule and taking note that your capital XK is related to your displacement. So we know that the displacement is simply small x minus big X then. Okay, so if we want to get the big X, we simply get this one, small x minus u. Okay, and some transformation on the partial derivative of a vector of position with respect to itself is simply an identity matrix here. And since in structural applications we always assume very small displacement in comparison with the geometry, the original geometry of a system. Say if the length of a beam is 6 meters, we don't expect 1 meter displacement then. So we only expect a couple of millimeter to be induced at a certain position. So we can now safely assume a small displacement assumption, and therefore this can actually be very small. If you take the gradient of a very small value, then that value vanishes, and we can say that the Lagrangian description for any field, no, any field uh, of motion is simply equivalent to the Eulerian description. So this just proves to us that linear momentum principle can actually be simplified with this assumption. So for the equations of motions, we have derived this a couple of times. We have encountered this, and let's just define that the linear momentum principle in terms of the equation of motion simply gives you uh, uh, the measure of the time rate of change of velocity of a particle in a continuum. Okay, so when you say a particle, we are referring to the mass. Okay, so this is the mass of the system, mass representation of the body, and we're talking of the rate of change of velocity. We are referring to the acceleration. Okay, and the mass times the acceleration is simply the force upon which uh, the motion of the system is actually uh, being dependent on. Okay, so simply this is simply mass times acceleration is equivalent to the summation of forces within the system. And the summation of forces is composed, of course, of the uh, surface force or the traction force and the body force. So in our day-to-day encounter of structural engineering on structural engineering analysis, we are just referring to the applied forces and the self-weight, okay, or the inertia forces. So this equation of motion is not new to us, so it was just presented in a different form. So the above equation can now be written in this form. Again, we can now uh, safely assume that we are referring to the Eulerian description here, as was defined earlier, or we can make use of this as your equilibrium equation. Okay, so again, we are considering here uh, the density as now the representative of your mass versus the forces. Okay, so here your body force is now equivalent to an Fi here, which is simply your raw Pi. Okay, so the above formulation was based on small displacement theory or small deformation theory, and therefore the following conversion to Lagrangian description is valid. Okay, so again, this is a Eulerian to Lagrangian, and if we want to use, instead of velocity, your second derivative of displacement, so these three uh, expressions here are equivalent. Also, so this is in terms of motion. So this is in terms of stresses. Okay. So in terms of stresses, we can say that the partial derivative of a stress field in terms of the Eulerian description is simply equivalent to the partial derivative in terms of the Lagrangian description. And so with the density, and so with the uh, body force. Okay, so this is the mass density, and this is the body force. So finally, the equation of motion now can be um, stated by simply using the displacement as your uh, variable of concern on the definition of your acceleration. Okay, so since this is still acceleration times the mass is equivalent to the summation of forces within the system or the body. Okay, for the strain displacement relation, the relationship between the Lagrangian linear strain tensor Lij and the displacement gradient Ui comma j. Okay, so take note the comma there has something to do with the partial derivative operation. Okay, so we have discussed this in the previous concept, and it's defined in terms of this infinitesimal strain description. Okay, so remember the finite strain is the more accurate. So if we are using a small deformation assumption, then we neglect the product upon which these two expressions here produced a very small negligible value, and therefore for very small strain, the product term will be negligible. Okay, so note that I comma j denotes a partial derivative operation. So let's talk now on the compatibility equation for linear strain components. So compatibility equations are very important for counter-checking the consistency upon which the particles are moving. No? In simple terms, if you do a tension stress on a member, you don't expect the member to contract or to compress. No? So it must be compatible. The strain motion should be of the same nature in terms of magnitude and sign with that of the given stress. So that is in simple terms. But if we are talking with very complicated situations, then we need to come up with a initial format in order to check if the compatibility equations for the strain components are satisfied. Okay, so we note that the linear strain as defined here in terms of infinitesimal consideration has six components or six equations, namely this one, L11 is simply equal to U11, no? So if you add U1 comma 1 plus U1 comma 1 divided by 2 is U1 comma 1, and so on and so forth. So these are all uh, defined very easily in terms of the components. And the right hand sides are determined, this part here, by three displacement fields or relations. Okay, so if you know these three displacement uh, description or field or relationship, then the strains can actually be obtained. But in the other hand, if the strains are determined first, then we have six equations to rely on to determine the three unknown displacements. So how is that going to be fair? No? So you have six available equations and you only are bound to get three unknown displacement, then it should be that the other linear string components must be compatible, and that's the use of the equations of compatibility in order for us to assure ourselves that everything is fine. So the particles moving inside the body is perhaps undergoing a logical, okay, motion by simply doing a check on these equations of compatibility. So the equations of compatibility was derived from many books. Of course, one of them is from Chang. So I got this from Chang. So I have not placed it here. It's just all about the use of some mathematical preliminaries, no? And it will arrive at this equation here, which is simply called the equations of compatibility. So since we have four index, okay, we have four index. The first two here and are actually index upon which the strains are defined, and the last two KL are the index upon which the strains are derived with respect to. Okay, so you expect now a 3 to the 4 81 components. So you have 81 components, or simply 81 equations in this particular uh, expression here. Okay, so they are all consistent. Okay, so you have an IJKL index. But for these 81 equations, only 6 are distinct or independent. Okay, the others are dependent on the other. So they are, in other words, they are just equivalent. So we don't need to check them because they are just a replication of the others. And so these 6 equations written now below are sufficient for us to assure compatibility in terms of the motion of the particles inside the body. Okay? In fact, in 2D analysis, this will still be reduced to a smaller, no? Say, if that is 2 to the 4 is 16, no? So I think there will only be around 2, okay? 2 distinct, separate, and independent equations that we need to check in that regard. Okay, note that the Eulerian form can be written in the same format. So L means Lagrangian. If you are using Eulerian, you just use letter E. Okay, so E11, sorry. In the Eulerian, and they are just actually the same if you are using small deformation theory. So this is simply Eij, comma KL is simply equal plus KL, comma Ij equals EJK, comma IL plus EIL, comma JK, something like this. Now, if you are doing an Eulerian form, so you might as well use the letter E there. So we know now the linear uh, strain equation or relationship. We also know the compatibility equation. So we are bound to look into some more equations to be used in your stress analysis, strain analysis, uh, which is known as the constitutive equations. Okay, and these constitutive equations are backed up equations in order to solve completely the unknowns, whatever are the unknowns given in the problem. Okay, so for a linearly elastic solid with constant density and known body force, we have 9 basic equations, and they are the equations of motions. Okay, so this is now simply your equilibrium equation. And these are your strain relations, strain displacement relations. So if you have three equations of equilibrium. So we know that summation forces uh, at a certain direction, I, j, and k, etc. So you 1, 2, 3 rather, if you are using an I here. So you have three equations. You have six equations for your strain displacement uh, relations to be checked using the compatibility equations. So you have a total of 9 basic equations considering motion. Okay? And from these equations, there is a total of 15 unknowns, which is 6 strains, 3 displacement, and 6 stresses. So we need 6 more equations. So 15 minus 9, we need 6 more equations uh, in order to solve totally the number of unknowns. Okay? And we get that from the constitutive equations. Note, we cannot get this remaining needed equations from the compatible equations because compatible equations are merely restrictions. They are just used to check if the nature of motion within the body is valid or compatible. No? Uh, how do you know that? No? So a rigid body, a solid body class, when the particles are moving from one time, let's say t initial to a t final, there must exist the same configuration of having no gaps or spaces on the final stage or the instantaneous stage. And if these compatibility equations, one or a few of them are not satisfied, then there's something wrong with your formulation. And that's why you need to check always these compatibility equations uh, in that regard. So note, if in case you assume some gaps, let's say some cracks inside the body to have occurred, okay, then still compatibility equation must prove. Likewise, in order to make or to comply with those restrictions you have placed in your model, okay, that's why you are modeling something. Uh, Imagine if you have an initial crack and then you want to prove that that crack will close upon inducing this particular force in this direction and so on and so forth. So that has to be proven in terms of compatibility equation. But this compatibility equation cannot be used as an additional equation to fill up the uh, remaining equations that uh, is needed to complete the solution for these 15 unknowns. So take note of that. So if we recall from elementary strength of materials, for a uniaxial state of stress, we know that your sigma ij is 0 for I and j not equal to 1. Meaning to say, in a uniaxial state of stress, you only have one axis, and that is axis 1. And therefore, your constitutive equation is simply sigma 1, 1 is equal to a constant of proportionality E, which is what? This is simply your constant of proportionality multiplied by the strength. Okay, so or if you want to make the familiar notation, simply this is sigma over epsilon. Okay, so this is for a uniaxial state of stress. So constitutive equation is an extension of Hooke's law. It is a Hooke's law in more than one dimension, okay? Which states that stress is simply proportional to strain. So if we want to make use of a term, generalized Hooke's law, to change, no, the name of this as your constitutive equation, we now refer to this word generalized Hooke's law as your constant of proportionalityCijkl to be used in this relationship. Okay, so sigma ij now is simply equal toCijkl of your LKL. Of course, temperature effect is neglected in this regard. So whereCijkl are simply the constants of proportionality in terms of what order? Anong order nitongCijkl? Okay, so this is now a what? Huh? What's the rank or order of this tensor?
Four.
Yes? Quences, anong order ng tensor natin?
First po.
Ah? I cannot hear you. Make your audio louder, please.
First order po, sir.
First order. So, who says otherwise? Aiko, anong order natin doon? Hanggang ngayon yung order, may doubt pa kayo sa sarili nyo? Ah? Rank and order. Nasa ano na tayo? Halos last part na tayo. Meron pa rin kayong doubt? Doon sa paano nakukuha yung order? Ah? Yes, Jeff? Ano yung order natin, Jeff?
Yung, sir, second order.
Ah?
Second order po.
Mahina yung audio mo.
Hello, sir. Second
Yes,
order,
yes.
sir.
Yes.
Second order po.
Yes.
Second order, sir.
Hindi ko marinig. Okay, John, what's the order of the equation?
Sir, dahil magkukulapse po yung dalawang
Hindi, yungCijkl ang tinatanong. Yung Kijkl.
yung equation. Fourth po, sir. Fourth.
Dali. Ako ata ang mahina ang audio ko. Sandali. Ayun. Sorry, class. Ako yung mahina. Okay. So, yan. Rinig ko. So, ilan yung Kijkl? Order nito, ilan?
4.
Ha? Ilan?
4.
Okay. Fourth order. No? Fourth order.
For index.
Kasi bibilangin mo lang yung index, gano'n, no? So, kung di na pa naiintindihan yung order, basahin nyo uli panoorin nyo uli yung video natin do sa first, no? Para nang di na kayo nadilito. Okay, fourth order. So, ilan na, ilan na components? Ilan ang laman nung tensor mo? Kung fourth order yan.
Sir, 3.
Ah?
81.
Okay, 81 tayo.
3
Okay, so 81. So 3 raised to 4. So kailangan alam niyo na 'yan, no? Kasi dyan kayo magdi-depend class when you are doing the program, doing the computation. Okay? Importante yan. Okay, for the case where sigma ij and LKL are symmetric, okay, meron tayo ngayong, anong tawag dito, yung leverage, no? So, dahil symmetric siya, yung 81, pwede mong bawasan ng 36 elements. So, yung iba, ibig sabihin, hindi mo kailangan. Okay? Hindi mo kailangan. Kasi ang kailangan mo lang, yung symmetrical component niya. So, let's say, meron kang symmetric ang laman nito, ito lang. Ito lang ang kailangan mo. Ilan ito? 6, tama? 3 sa diagonal, 3 sa off diagonal. Huwag mo na pakialaman ito kasi symmetrical siya. So, liliit yung kailangan mong array memory, no? Sa computer. So, I'm not talking of the advantage on computer programming. Of course, if you want to do it this way, you can do it. Okay, so you can convert this into a vector of 6 elements. So, magiging siyang, ito, 1, 1, 2, 2, 3, 3. Okay? So, tapos ito is 2, 3, 1, 3, 1, 2. So, ang pag-vectorize nito class, pag ganito, no? You can do it your own, pero sa mga nakita kong reference, pababang ganyan, no? Pag ganyan, no? Pababa. Tapos, aakyat ka doon. Okay? Tapos, pupunta ka dito. So, ibig sabihin, pag binectorize ko ito, magiging 11, 22, 33, 23, 13, 12. Yan. Yan ang basa mo dyan. Okay? So, para pag nagpo-program kayo, yan. Okay. So, kung kabisado nyo ito pwede kayong gumawa ng research on how to analyze let's say a solid model or a two-dimensional model if you want. Pero mas maganda solid na pag ganito. And then make some experimental study on strains, okay, relationship, and come up with the statistical anong tawag doon? Determination, okay? Statistically, you determine your constant here in this form. So, vectorize mo siya para hindi ka mahirapan sa programming because it needs a lot of trial and error on the to make sure that the compatibility equations will be satisfied. Okay, so those are just thoughts for you to ponder. Siyempre, mahirap gawin yan pang research na yun. Okay, so the components of the stress and strain can be re-indexed. Ito na yung sinasabi ko, no? So, re-index mo, ganyan na siya. So, magiging 6 vectorial na yung ano mo, yung operation mo. So, vector to vector. So, ito na ngayon. So, this is now your equation. So, it's a stress vector with a generalized constant. Okay? So, ngayon, ilang elements na lang ito? 36 na lang ito. Tama? Kasi 6 by 6, 36. Ito vector na rin to. So, this is 6 by 6 matrix. Okay, note that your C11, if you are referring to alpha beta, is equal to C1111, C22 is C2222, C33 is C3333, C12 is C1122, C14 is C1123. Paano nakuha to? How can you Okay, so paano mo siya malalaman kung ito yung laman niya? Ano ba yung laman nung C? originally, ano yung laman ng C? Yung laman ng C class, 81 yan, di ba? 81 components. So, meron kang C dito. So, kung hindi nyo na-imagine yung sinasabi ko, so tignan nyo ito, ano? Meron kang hindi tama yung pagkakasubdivide. Ayan, no? So ito yung CIJKL mo, no? Ito yung CIJKL. Ayan. Can you imagine it? Paano naging 81 ito? Ilan ang laman sa loob nito?
3 bytes, sir.
Okay, 3 by 3 pa yan, no? 3 by. Importante ito kung gusto niyo mag-engage sa programming class. Ngayon, kung hindi niyo naman hilig talaga, hindi niyo ma-appreciate yung ano nito, ano, discussion. Okay, so tig siyam ito, no? 3 by 3. Kaya naging 81, tama? Tama, class? So, nag-gets nyo na yung laman. Ayan, ganyan siya. Ayan. Ayan. So, yan yung laman niya. So, kung wala, nag-experiment ka, gusto mong malaman yung gusto mong malaman yung property, yung elastic property ng isang material, isang member, tinest mo, nakuha mo yung strain, nakuha mo yung stress, masosolve mo to, no? Pero syempre, pag tinest mo ulit, iba na naman. So, yun yung sinasabi kong pwede mong gawing study ngayon yon. Diba? So, kaya kung naiintindihan nyo lahat yung topics natin dito, lalo na dito sa mga core courses na to, imposibleng wala kayong maisip na research class. Ang problema lang, talagang medyo pag-uukulan nyo ng panahon, no? Matakaw sa oras, pag i-prepare yung mga yung proposal ninyo, no? Okay. So saan yung C1111 diyan? Saan diyan? Anong parte yan? Kuwari, I ask you, please pinpoint saan diyan yung C111. Asan? Di ba IJKL yan? Kuwari, IJKL. Asan ba yung IJ mo? Okay, so depende kung paano mo dinefine. Kunwari, ito yung I row ko, I row. Ito yung I rows, I na row, ito yung J ko. Tapos dito naman, meron akong KL. Individual ito, ano? KL. So, ganun mo titignan yan, class. KL. Kaya pag sinabing C11, ibig sabihin, yung I tsaka J mo, 1, dito ka. Saan particular dyan? 1, 1 pa rin. So, ito yun. Ito yung C1111. So, did you get it?
Yes, sir.
Okay. So, yun lang ibig sabihin na, no? Okay? O, kunwari, dito tayo sa medyo ano, ito pala, wag niyo muna pansinin ito. Yung definition lang nung green tsaka Cochito, ano? Sorry. Yung engineering component, ayan, G yung green, Cauchy yun. Tapos, kaya lang may 2 dito, dinidefine na natin yung normal engineering shearing strain. Yung sinabi ko dun sa pagtinuro sa atin sa strength of materials, yung strain natin, imbis na ganito, nagkakaroon ng yung gamma mo dito, yung gamma mo kalahati pag ganun yung hinila, no? So, meron kang gamma dyan, gamma over 2 dito, yun lang yung ibig sabihin nito, no? So, dito, yung ano mo is already 1/2. 1/2 na lang nung total na gamma. Gamma over 2. Gamma over 2. So, yun lang ibig sabihin nito. So, huwag niyo muna pansinin to. Dito muna tayo. Wala, C1123. Saan yon? So, C1, 1. Okay, 1, 1. Dito pa rin siya, no? Saan yung 2, 3 mo? So, kumuha ka ng pangalawang row, tapos ito siya, no? Ito yung C1, 1, 2, 3. Ay, baligtad. Although symmetric siya. Okay. So, C1, 1, 2, 3. Yan. Parehas lang siya, no? C1, 1, 3, 2. Ito. Okay. Parehas lang siya niya. Okay? So, parang ganun yung ibig sabihin nito. So, pag binigyan ko kayo ng problem, binigay ko ito, alam nyo kung saan nyo pupulutin ito. Okay? Ngayon, bakit C14 ito? Paano mo naman, ito C14 mo, it refers to C alpha beta. So, alpha beta to, no? Alpha beta. Yung vectorized na ito, na-gets nyo? Yun na yung sigma is equal to C alpha beta times another vector. So, 6 na to. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? So, pag sinabi mo C14, C1, tapos 4 yung ano mo dito. Okay? So, C14. Saan dito yung C14? Kung ito yung 1, 2, 3, 4 mo, 5, 6. Ito yung 1, 2, 3, 4, 5, 6. Saan mo siya saan siya nakabilang dito? So, C14 is 1, 4. Dito siya nakatama. So, itong C1, 1, 2, 3, tamang-tama siya dito niyan. Gets? So, doon siya ipapasok. So, kasi meron ka ng conversion from, ayan, reindexing from a CIJK of 81 elements to a C alpha beta of 36 elements. Okay, the first 4 constants are for normal components. Ayan. Ito, normal components kasi mapapansin mo, nandun siya sa diagonal panay. Nasa diagonal pag normal. Pag nakakita kang off-diagonal term, ito, shear ito. These are for the shear components. Okay, so that's it for an introduction on the elasticity concept. So,